Today, we will have Professor Wolfgang Altmannshofer from University of California, Santa Cruz, tell us about the state of the decay anomalies. So please.
Thank you. Thanks a lot for the invitation. Yeah, it's always a pleasure for me to talk about the B anomalies. They have been around now for several years, and what I will try to do in this talk is to give a broad overview of the various results that are out there that disagree with standard model predictions, and I will try to argue why that might be why these various anomalies actually could be a very interesting and consistent picture of new physics that is starting to show up in this rare B decays. So let me start by just going very roughly over the general picture. So we will be talking mainly about these types of rare decays. So we have a B quark decaying into a strange quark, and then a lepton anti-lepton pair in this picture here. It's a muon anti-muon, and so that is a flavor-changing neutral current process. In the standard model, such a process is forbidden at the tree level, but it is induced at the one loop level. And shown in the middle here is one example of a standard model diagram that contributes to this B to S mu plus mu minus transition, and it consists of a loop that includes a top quark and a W boson, for example. Now at the energy scales where this process is happening, that would be the energy scale of the B quark or of B mesons, the energy is not large enough to actually resolve those particles in the loop, though it is effectively described by a 4-fermion contact interaction between the B quark, the strange quark, and then the two muons. And that one can then try to do at a very basic level is to determine experimentally what for example, the rate of such a process is, or what the other properties of this process is. So in the end, one tries to measure what this 4-fermion contact interaction is, what the value of that coupling is, and then one can also predict that effective interaction in the standard model, and can try to do that as precisely as possible. And then one can compare those two things. If the experimental results agree with standard model predictions, then one would get a constraint on possible new physics contribution to this process. And on the other hand, if there's a disagreement, if there's an anomaly, so if there's a disagreement between the standard model prediction and the experimental measurement, then one could attribute that to a new physics effect and try to understand which type of new physics couplings or new physics scales could be responsible for such a discrepancy. And very generically, one could parameterize these new physics contributions again in terms of effective interaction, for example, 4-fermion contact interactions, and then the typical scaling of this new physics effect would be some new physics coupling divided by a new physics scale squared. And so if one has then anomalies in these types of rare B decays, then one could establish a new scale in particle physics. So if one assumes that there's an order 1 discrepancy between the measurement and the standard model prediction, the new physics scale that one can estimate, assuming that the new physics coupling is of order 1, is around 10 TeV or so very, very roughly. And that is actually an interesting scale. On the one hand, it's not necessarily clear that such a scale would be directly probed at the LHC. So whatever new physics is responsible for such an anomaly could very well be outside the reach of the LHC, but it is not so extremely high that it could be completely invisible to us in the future. So it is conceivable that we will be able to build colliders to directly probe whatever new physics is responsible for such anomalies. So that's a very rough basic picture. On the experimental side, we have the LHC, which is a B factory. So what is shown in the plot on this slide here is the integrated luminosity recorded by the LHCb collaboration, and the data that they have accumulated so far, something like in total 9 inverse femtobarn, 3 or roughly 1 inverse femtobarn at 7 TeV, 2 at 8 TeV, and then 6 at 13 TeV. That corresponds to more than like 10 to 12 B quarks that have been produced. So LHCb is very sensitive to many rare B decays, and in many cases LHCb has made first measurements of processes that are very rare, and for example were not observed at the B factories, or could make very precise measurements surpassing the position at the B factories. And all those measurements, or many of those measurements, they actually show discrepancies with standard model predictions, and shown in this plot here, sort of a summary of various measurements that show discrepancies with standard model predictions, and they are shown here in this plane of significance, and then on the y-axis, what is written here is the relevance of hadronic effects. So that in some sense is the how theoretically clean an observable is. So the higher up it is in this plot, the cleaner, theoretically cleaner the observable is. So in some sense you can think of it as how much you can actually trust this sigmas on the x-axis. And there are various classes of processes listed in this plot. Up here we have Rk and Rkstar. These are lepton flavor universality ratios. These are ratios of branching ratios of rare B decays, B2K LL or B2K star LL, and one compares electrons or muons in the final state, and we will discuss this in more detail in a few minutes. But those are probably the theoretically most clean measurements, and they deviate by 2.5 to 3 sigma from the standard model predictions. There are very other observables also related to B2S LL flavor change neutral current decays that show this anomalies. These are, first of all, absolute measurements of branching ratios. Branching ratios of B2K mu, B2K star mu, vis-a-vis to phi mu. They all differ from standard model predictions at the level of 2 to 3 sigma. There are angular observables in B2K star mu, famously the observable called P5 prime. Also that one differs from standard model predictions by 2.5 to 3 sigma. There's also the purely leptonic decay vis-a-vis to mu. This branching ratio is maybe a 2 sigma tension or so with standard model predictions. And so all these processes that are circled here in red, they are all related to the same B2S LL transition, and they all show discrepancies. And what I will argue later in the talk is that this pattern of discrepancies fits very well into a new physics picture. There are other anomalies in B decays. There are the anomalies called RD and RD star. These are again lepton flavor universality ratios, but not in flavor change neutral current decays, but now in charged current decays, B to charm L nu transitions. And there one compares decay modes with taus in the final state to decay modes with light leptons in the final state. So those measurements, they for the first time an anomaly observed in those was already quite some time ago. I think it was 2012 by Babar. They saw their discrepancy, and since then there have been additional measurements by Bell and also by LHCb, which don't see as large a discrepancy as Babar, but overall there still seems to be individually a 2 to 3 sigma discrepancy also in those lepton flavor universality ratios. In this talk, I won't spend much time on these charge current anomalies. I will mainly focus on the B2S LL flavor change into current decays. For comparison, I also put in this plot the G-2 of the muon. Very recently there we got these exciting new results from the from the Fermilab G-2 experiment, confirming the old anomaly observed there at Brookhaven. It's a more than 4 sigma discrepancy if one trusts the standard model prediction that is typically quoted. And I just wanted to put that as a comparison, though, in terms of significance, G-2 is higher than all those rare BDK anomalies. And in terms of, let's say, theoretical cleanliness, I would put it somewhere in the middle. I don't think it is as clean as these lepton flavor universality ratios, Rk and Rkstar, but it is, I would say, definitely cleaner than those, for example, branching ratio measurements of B2K mu, B2K star mu, and B-sub-S to phi mu. And it's probably somewhere around the P5 prime observer, or maybe slightly cleaner than P5 prime. In my opinion, G-2 is some very interesting observer as well. But again, I will, it will come back. We'll come back to G-2 at some point in this talk, but I will mainly focus on this rare B decay anomalies. All right, so let's go into more details and discuss these various entries in this plot that I just showed. So let's start with this purely leptonic decay of a B-sub-S into mu plus mu minus. Arguably the simplest rare B meson decay that one can look at. We have the B-sub-S meson decaying in this two-body to this two-body final state made up from muon and antimuon. And experimentally, what one does, one looks for muon-antimuon pairs and tries to see a bump in the dimuon invariant mass spectrum at the mass of the B-sub-S meson. And what is shown here in this plot here is an average of the various experimental results. It is presented in the plane of the B-sub-S to mu plus mu minus branching ratio and the B0 to mu plus mu minus branching ratio. And these branching ratios in the standard model, they are predicted in the case of B-sub-S to mu plus mu minus a few times 10 to minus 9, and B0 to mu plus mu minus predicted around 10 to minus 10. And the various experimental results, they sort of line up in that in the vicinity of the standard model prediction, but there is some sort of 2 sigma-ish tension between standard model and experiment. So in particular, the B-sub-S to mu plus mu minus branching ratio, as measured by Atlas, CMS, and LHCb, is just below 3 times 10 to minus 9 or so, while the standard model prediction is more like 3.6 10 to minus 9. So that's a slight tension. The measurement is slightly below the standard model expectation. This by itself is not super exciting, I would say. I mean, if this was the only discrepancy, nobody would talk about an anomaly here. But as you will see, it fits very nicely in a consistent picture of all the other anomalies. Instead of looking at this purely leptonic decay, we can look at semi-leptonic decays. So now we have a B2S mu transition where some strange flavored hadron is in the final state. One example is shown here. We have a charged B meson decaying into a charged kaon and a muon and antimuon, but one can also look at other versions of that. One can look at the neutral B meson decaying into a neutral kaon, plus mu minus, or one can look at the B-sub-S meson. One can even look at baryonic versions of that decay mode, where we have a lambda B baryon decaying into a lambda and a mu plus mu minus. If one now looks at the branching ratios of those semi-leptonic decays, one finds again that the experimental results are below standard model predictions. What is shown in these 3 plots are the differential branching ratios as a function of Q squared. Q squared is the invariant mass squared of the 2 muons. And these various colored bands are the standard model predictions, and then the various crosses here are the experimental results. Then one sees that consistently across the various decay modes and across a broad Q square range, the measurements are below the standard model predictions. And that is at the level of, these discrepancies at the level of 2 to maybe 3 sigma, depending on which standard model prediction one is actually using to compare the data to. This p sub s to phi mu measurement, that is actually something very recent that just came out a couple of months ago. So, and yeah, just to highlight again what I just said, the size of this discrepancy depends crucially on what one assumes about the standard model prediction. So if one only uses light consum rule calculations to make a standard model prediction, one gets these blue boxes here, while if one takes into account lattice determinations and light consum rule calculations of form factors, then one gets these red boxes. One can wonder how reliable these various calculations are in different Q-square regimes. And one can have a lot of debates of how reliable these standard model predictions are, how reliably one can estimate the uncertainties on those predictions, and depending on what one does exactly, the significance of this discrepancy is somewhere between, I don't know, 3 sigma and then maybe 2 or 1.5 sigma or something like that. So there's a large dependent on which assumptions one makes about the standard model prediction, how conservatively one estimates the uncertainties there, how one models certain non-factorizable effects, etc. If you look at the B2K star, U plus U minus decay, one can look at a large set of observable in this decay mode. So here again a sketch of how this decay looks like. We start with a B meson. Here it's a neutral B meson, which is a B quark and an anti-down quark in it. Decays into the K star, an excited kaon with a strange quark and the anti-down, and this excited kaon decays into a charged kaon in the charged pion, and then also the mu plus mu minus as before. That at the quark level, it's again the same B to S mu transition as we have been looking at so far. Now that we have these 4 particles in the final state, there are several angular observables that one can look at. These 4 body final state is characterized by in total 3 angles. And then one can look at the angular distributions in those 3 angles and not only predict the rate of that process, the branch nature of that process, but also these angular observables. Here's just an event display how such a B2K star mu plus mu minus decay looks like. I don't know how well you can see that on the screen, but one has here this primary vertex where the proton-proton collisions occur, and in that case a BB bar pair was produced. One of the B quarks hydronized into a B meson, traveled here to this secondary vertex where it decayed into the mu plus mu minus in a K star, and this K star immediately decayed also into a kaon in the pion, and this kaon pion and the 2 muons, they all point back to this secondary vertex that is clearly identified in this event here. And yeah, as I said, now one can look at the various angles between those 4 decay products. One can look at the let's say the angle between the kaon and the dimuon system, or the angle between one of the muons and the K pi system, or one can look at the angle between the 2 decay planes that are spanned by the mu plus mu minus and the K pi, and that way one can construct a generic angular distribution and measure the various coefficients in this angular distribution. So essentially, what one does is one measures moments of this angular distribution, if you like. And one of those moments of the angular distribution, or better, a certain combination of moments of the angular distribution, that is what is referred to as P5 prime. And this P5 prime observable doesn't agree well with standard model predictions. That has been the case since the first measurements of P5 prime, going back, I think, to 2013 even. Here's the situation in 2015. That was I think the update with the full run 1 data. And so in 2015, we already had something a 2.5 sigma discrepancy between the LHCb measurement, these black crosses here, and the various standard model predictions, either the orange or the purple boxes. And there are various other measurements of P5 prime at that time, already from Atlas, from CMS, also old Bell results. They all had quite a bit larger uncertainties than the LHCb result. So if you do some naive combination of those various results, you find that it is dominated by the LHCb results, which show some visible discrepancy between standard model predictions and data. Again, as before, let me stress that one has to discuss what are the standard model uncertainties in those predictions. Here one sees these two standard model predictions. Again, depends on how exactly one treats hadronic effects, how one parameterizes certain, how one models certain non-factorizable long distance effects, and depending what one does exactly, depending how conservatively one tries to estimate uncertainties, one gets slightly different results, and depending on what one does exactly, one also gets different, slightly different significances of how big this deviation is. But still, the standard model predictions that exist, they tend to be low compared to the data in this Q-square region. Now, with the time, the measurements have been updated with more data. So last year, this is the result for P5 prime now with the full run 1 data plus part of the run 2 data. And again, the situation is such that this anomaly persists. The central value shifted slightly. The uncertainties got quite a bit smaller. Standard model predictions again have uncertainties that one can discuss. What one sees here is that the standard model uncertainties have roughly a similar size as the experimental uncertainties. So here one now can start asking what will we actually learn when the precision on P5 prime, once the experimental precision on P5 prime gets better and better, and probably will start now to be dominated by the theory uncertainties in this context, and there will be always debates of how well under control this theory uncertainties actually are. In any case, this P5 prime measurement is done in the neutral B meson decay, when there's a neutral B meson decaying into a neutral K star and mu plus mu minus, and then the K star going into a charged K and a charged pion. That's the most easy channel to look for experimentally at LHCb. But they also have a measurement from half a year ago or so, which looks at P5 prime in the context of charged B meson decay. So now you have a B plus or a B minus decaying into a charged K star and mu plus mu minus, and the charged K star can decay either into a charged pion and a neutral kaon, or a charged kaon and a neutral pion. And those neutral kaons and neutral pions, they are much more difficult to detect at LHCb. So there the efficiencies are much lower, the statistics is much lower. Therefore, these measurements have much larger experimental uncertainties. It is essentially consistent with standard mode predictions, but also consistent with the P5 prime results from the neutral decay mode. And one sees here the same trend as in the neutral decay mode, that the measurements are above the standard mode predictions in this Q-square region here. So in some sense, if one tries to quantify that, they claim they do see also this anomaly in the charged decay mode in the same way as they see it in this much more preciser measurements of the neutral decay modes. Okay, then the last class of observables that I would like to discuss, these are these lepton flavor universality ratios, Rk and Rk star. I already mentioned that these are these ratios of branching ratios of B2 K mu mu or B2 K star mu mu over B2 K EE or B2 K star EE. this is a situation as of last year. There were measurements of Rk and Rkstar, measurement of Rk in one Q-square bin from 1 to 6 GeV squared, and then 2 bins in the case of Rkstar, one very low Q-square bin below 1.1 GeV squared, and the other one from 1.1 to 6 GeV squared. And all those measurements were low compared to the standard model prediction, which is around 1. And because very excitingly, a few months ago, there was this update from LHCb of Rk, now with the full run 2 data. And they confirmed the central value that they saw previously, central value around 0.85, now with uncertainties of around 0.04. And they claim a 3.1 sigma deviation from the standard model prediction, which is 1 with very small uncertainties. So that is very exciting. As I mentioned before, those observers, Rk and Rkstar, they are now theoretically very clean. There's very little uncertainty in the standard model prediction. So this is something where one can clearly point to new physics if those things persist with more data. And so this update of Rk from LHCb is very reassuring that by adding in more data, the central value stayed where it was before, and the uncertainties went down as one expects from the amount of data that they added. So that is very reassuring that this significance of the deviation now is increasing. And of course, I would like to see that continuing with future runs, and also in Rkstar, where the current result is still based on the run 1 analysis. So there one is hoping to get an update soon. And again, because we will hope that the central values stay significantly away from the standard model prediction, and we get a higher significance also in Rkstar compared to what we have now. Okay, I mentioned that the standard model prediction for Rk and Rkstar is pretty robust. So let's just go through that argument why that is the case. At the zeroth order, one expects that Rk and Rkstar should be 1. The only difference in those 2 decay modes is the flavor of the lepton and the leptons in the final state, electrons and muons. The masses is the only thing that distinguishes electrons and muons in the context of the standard model, and those masses are much smaller than the typical momentum transfer in such a decay of a B meson into a K and or K star and into leptons. So at zeroth order, that should be 1. And then there will be small corrections due to the fact that the muon actually is more massive than the electron. So due to phase space effects, one could expect some correction of the order of the muon mass squared divided by Q squared, again, which is the invariant mass of the 2 leptons in the decay. But that's a tiny effect. So unless one goes to this very low Q square bin, where there is some effect which is maybe non-negligible, but in this, let's say it's a 1 to 6 Q square bin, this is a tiny effect at the per mil level actually. And then all those hadronic corrections which come into play in the individual branching ratios, those hadronic corrections, they all cancel in this ratio of the B2 K or K star mu over B2 K or K star EE branching ratios. And those hadronic corrections is let's say parametrically of order lambda QCD over the B mass or order alpha S corrections. Those are only relevant to the extent that there are these phase space effects, so that this cancellation is not perfect. There are these tiny per mil level leftover terms which are very uncertain, but because they are tiny, one doesn't really care how big the uncertainties are in the end. Probably the largest concern in the prediction for Rk and Rkstar would be QED corrections. Because electrons and muons have different masses, they radiate photons in a in a non-universal way. Electrons radiate much more photons than muons, and very naively one could write that QED corrects in the following way. One would have some alpha electromagnetic over pi, and then potentially a double logarithm of something like electron mass squared over muon mass squared. And in reality, that's actually not what happens. The way the analysis is done and the way the experimental cuts are done on the masses and invariant masses and energies of the various particles involved, this logarithm is actually much smaller, and these QED corrections are actually at the few percent level, and they actually can be they are taken into account in the analysis, and arguably in a reliable way. So these QED corrections, they do seem under control, at least at the level of the total rate. And this has been studied and looked at in quite some detail. And then the typical standard model predictions that one quotes for Rk and Rkstar, at least in this 1 to 6 GV squared bin, are 1 with maybe a 1% uncertainty. And then in this very low Q square bin for Rkstar, there one does have some effect of phase space. So there it's not 1, but maybe it's something like a 0.91 with a slightly larger uncertainty, which is quoted here as 3%. If one goes to the differential levels, if one tries to look at, let's say, angular distributions and compare angular distributions of muons with electrons, there one could have potentially larger QED effect. So I guess this is something which should be studied in more detail in the future once there will be experimental results.
Excuse me?
Yes.
May I ask you a question?
Sure.
Another question. So, how can I understand that hadronic corrections are always multiplied by mu squared?
Yes. So if you assume that electrons and muons have exactly the same mass, and then you look at Rk, let's say the way it is defined, you have the branching ratio of B2. Now let's go back maybe to the previous slide where I have the expression. Here we have these ratios of branching ratios. So both the numerator and the denominator both have large hadronic corrections, and they are not very well understood how big they are exactly. But because you take this ratio, these hadronic corrections which come from QCD, and QCD doesn't care about the lepton flavor, they're exactly the same in the numerator and denominator, so they cancel almost exactly. They only don't cancel precisely because the muon and electron have slightly different masses, so it's not a perfect cancellation, but it's an almost perfect cancellation in those hadronic corrections. Does that make sense?
Okay, thank you.
Okay. Yeah, I think that is pretty much the story here. So the standard model predictions for Rk and Rkstar, they are very robust, at least for unless one is in this very low Q square regime, and uncertainties are probably at the percent level or so, much smaller than the let's say the discrepancy in the Rk measurement, which is at the level of 15% or so. Okay, so what could it be? We went through these various observations, various measurements. So now we can discuss briefly of what could be behind those various anomalies. There could be experimental issues. Maybe I'm not an experimentalist. I'm a theorist, so I don't feel qualified to comment on that. I'm not aware of any experimental issues that could explain those things. But who knows? This is something that I can't fully exclude, I guess. Could those be statistical fluctuations? In principle, yes. I mean, each single one of them comes with a significance of 2 to 3 sigma, let's say. Though it is conceivable in each individual case that this is a statistical fluctuation. But as I will argue, they come together in a very nice, consistent way. So it's somewhat harder to imagine that all of them simultaneously are statistical fluctuations that show this very intriguing pattern. But at least looking at them individually, it could be a statistical fluctuations, I guess. Parametric uncertainties, if you look at the meson estimate plus or minus rate and then the semi-leptonic rate, so these branching ratios, yes, they could definitely be behind that. With parametric uncertainties, what I mean here are things like CKM input parameters, for example, or overall normalizations of form factors or decay constants. Those things are relevant in those total rates or total branching ratios. And if those uncertainties and those input parameters are underestimated, then they could explain these discrepancies in the rates, or at least partially. The angular observables, so P5 prime and this lepton flavor universality ratios, they are constructed such that they are independent of such parametric input parameters, let's say from CKM matrix elements. So those couldn't be explained in that way. Certain underestimated hadronic effects, so these would be hadronic effects beyond form factors, certain long distance contributions that, as I said, have to be modeled in the context of these semi-leptonic decays, and they would impact both the rates but also the angular observables. So P5 prime is sensitive to certain hadronic effects which have to be modeled, and depending on what one does exactly there, one gets different results, and I guess one can't exclude that underestimated hadronic effects are causing some of these discrepancies. They couldn't explain the meson plus or minus rate, which the only hadronic parameter which enters there is the meson decay constant, and that's under fairly good control from the lattice. So these hadronic effects, I don't think they could explain meson plus or minus, and they also cannot explain these lepton flavor universality ratios Rk and Rkstar that, as I argued before, are almost insensitive, completely insensitive to these two hadronic effects. Then, of course, the most exciting possibility is that all these discrepancies are due to new physics, and this is the option that I will discuss now in more detail in the coming minutes. The basic philosophy that I will be following here is this bottom-up approach. So starting from the experimental results from these anomalies, one starts out with an Eft description of these various processes, either in the what is called the SMEF, the standard model Eft, which respects the full SU2 cross U1 gauge symmetry of the standard model in the unbroken phase, or the so-called LEFT, that would be the corresponding Eft below the electroweak scale, where one has only the U1 electromagnetism left, and then one just parameterizes the new physics in a as model independent way as possible. So making minimal assumptions, for example, that the new physics that is relevant for this effective interaction is heavy, and that this Eft description actually makes sense. And then based on these Eft studies, one can go on and construct simplified models. It introduces a set of new particles in the simplest possible way, so a minimal set of new particles, a minimal set of couplings, maybe a single leptoquark or a single C prime gauge boson, trying to get into a situation where one actually sort of has a UV picture where those effective field theory operators could come from. Then eventually one would like to UV complete that into something more motivated, some full-fledged model which addresses also other open questions in particle physics, for example, the hierarchy problem, or maybe the standard model flavor puzzle, or maybe has a dark matter candidate, and so one wants to ensure that this model is generalizable, UV complete, and doesn't have any weird features left over. So let's focus on the first steps, this Eft description. So this model independent new physics analysis. This is understood very well how this works. One writes down an effective Hamiltonian, including all the dimension 6 operators which can contribute to this rare B to S LL decays. And what is shown here in the slide are the various classes of operators that one typically considers. Are these magnetic dipole operators, BS photon operators, then one has semi-leptonic operators, one just has currents for the B2S transition and a current for the two muons, and depending what the chiralities are, these operators have come with different Wilson coefficients. So C9, for example, is the left-handed current for the B2S transition, and the vector current for the muons, and the C10 would be a left-handed current for the B2S transition, and the axial vector current for the muons. And then one has the corresponding primed version, so one has right-handed current on the quark side. And one also has scalar versions of these types of four-fermion contact interactions, where one has either p left or p right projectors in these scalar currents of the quarks and the muons. So that is a typical setup that one starts with. And then one looks at the various processes and the various observables within those processes, and realizes that many of these operators, many of these effective interactions, they simultaneously affect many observables in many decay modes. So there's a lot of complementarity in the measurements of those various observables in the various decay modes. And what it also means is one needs this framework of a global fit to really understand if there is any physics interaction that can explain the anomalies without introducing new discrepancies in other processes or in other observables that actually do agree with standard model predictions. And these global fits, they've become a sort of a small industry. So I've started doing that already before these anomalies were coming out. So already, I think more than 10 years ago, I started doing these global fits of rare decay data. But by now there are several groups which do these types of fits using different statistical methods, including different types of observables, different subsets of observables, using different ways to parameterize or model hadronic effects, etc. So there's a lot of cross-check between different groups and several different approaches, and they all more or less lead to very similar results, which is again reassuring. The simplest thing that one can do is to switch on one of those effective interactions at a time and see what one gets. And what is shown in this slide here is what happens when one switches on new physics in interactions with electrons. So one switches on now all the various four-fermion contact interactions, which include a bottom, a strange, and two electrons. And then what is shown in this table here is, on the one hand, the best fit value for these various interactions, for the Wilson coefficients of these various interactions, and then the pull value. That is the square root of the delta chi-squared between the best fit point in this physics scenario and the standard model point. And one sees that in these cases of these electronic operators, one can find scenarios where the new physics scenario does better by 4 sigma than the standard model point. And that is simply due to the fact that in all those scenarios, one can explain Rk and Rkstar. These are these 3 bins, these 3 measurements, Rk measurement 3 sigma away, and then the Rkstar measurements, both are 2.5 sigma away. So if you combine that in this context of a global fit, you get this more than 4 sigma pulls in those new physics scenarios. And to get an idea of how big this effect is in terms of the absolute sort of new physics contribution to those decays, the units, in those units that are shown here, the standard model values for those Wilson coefficients, C9 and C10, are around 4. And these best fit values for these Wilson coefficients, well, depending on what exactly you're looking at, they're around, let's say, 0.4 and 1.4. So these are between 10 and 20-30% new physics effects that one needs at the level of the standard model amplitudes. If instead one puts the new physics into the muons, then one gets larger pulls. On the one hand, one can also now explain the slight 2 sigma tension in Pisa Western plus minus. and all those other anomalies in the B2S mu transition. So the various branching ratios of the semi-leptonic decays, B2K mu, B2K star mu, B to the to phi mu, and the P5 prime anomaly, they all can be consistently described if the physics is in this Wilson coefficient C9 or in this combination C9 equals minus C10. So in those scenarios, if one includes all the data, one gets pulls which are close to 6 sigma. So again, this pull that corresponds to the square root of the delta chi-squared between the standard model point and the best fit point in this new physics scenarios. The question is how much one should trust those results, and they of course depend on how one parameterizes the theory uncertainties, how conservative one is with these theory uncertainties, and if you don't trust the theory errors that we are using in our global fits, then you shouldn't trust this last column here. Then probably you should only take into account these lepton flavor universality results and the piece of S to phi mu branching ratio, which are the theoretically cleanest ones. Where one cannot argue around with standard model uncertainties too much. So in that case, one still gets these 4 or almost 5 sigma pulls in some scenarios. Now one shouldn't confuse these pull values with.
Excuse me.
Yes.
Before you proceed, I have one question. In the second column, you assume you impose the lepton flavor universality and the B sub S to mu mu data.
Yeah.
But for the B sub S to mu mu, I remember it could be also affected by O11 or 12, or I forgot how to call the pseudo-scalar operator, right?
That is true. That is true. I haven't.
Yes, does not contribute much to B2S mu mu compared to B sub S to mu mu.
That is right.
What happens if you, for example, if you don't include the B sub S to mu mu in the second column? Almost the same fit, or?
It's almost the same. The C10 and the Z9 equals minus C10, those numbers go down a bit. So those are more like 4 instead of 4.7 or 4.6. That's the only change that happens. And the assumption here is that indeed that the scalar operators, that they are not affected by new physics, so switching them off completely. You're right that B the best plus minus is sensitive to those, and so one could invoke those scalar operators to explain B the best plus minus by itself. And then there wouldn't be anything, any additional contribution to the global fit coming from it. And as I said before, in that case, those entries here, this 4.7 and 4.6 here, those would go down to 4 or 4.1 or something like that.
Okay, thank you.
But what I would like to stress here in this context is that these pull values, you shouldn't confuse them with sort of absolute significances of those anomalies. When one tries to do that, one has to take into account, for example, a look elsewhere effect or something like that, because there are many measurements that one is looking at. Many of them do agree with standard model predictions. So half a dozen or maybe a dozen even don't agree very well. There are these various anomalies. So there's some, given that there are many different processes, many different observers that one can look at, and many of them do agree with standard predictions, there's sort of some dilution of those anomalies, because one does expect just by chance that some of them will show discrepancies. People try to do this exercise, to do a careful job in estimating of what the actual global significance of all those anomalies is. And in this paper that came out a few months ago, they come to the conclusion that it's sort of the global significance of all those anomalies is around 3.9 sigma. What is now shown in this plot is a slightly different way of presenting the information of those tables, but now instead of switching on one Wilson coefficient at a time, it switches on 2 simultaneously. So in this example, C9 and C10. Again, these are defined as coefficients of these operators here, left-handed B2S transition, and as a vector or axial vector current for the muons, And then this blue band here, that is the best fit region that one gets by taking into account only the lepton flavor universality ratio, so only Rk and Rk star. There's some slight preference for C9 over, sorry, for C10 over C9, but there's this broad degeneracy, this very elongated band here, which covers a broad region of parameter space. And then if one looks at the various other measurements, if one looks at the B sub S plus C minus branch ratio, that gives this yellow band here. And then this various B to S mu observables, the branch ratios and the angled observables, they prefer this orange region here. And then the global fit is this red ellipse here with the corresponding central values quoted here. And yeah, just by eye, if you just extend that contours here, if you're delta chi-squared of, I guess, corresponding to a pull of 1 sigma, 2 sigma, then you get 3, 4, 5. So you get a pretty far distance from the standard model point, which is here at 0, 0. But again, this orange blob is something that you might argue does depend on hadronic effects, does depend on the modeling of hadronic effects, and maybe you don't fully trust that. So in that case, you should only trust the blue band and the yellow band. And then you're getting still something which is significantly away from the standard model, but not this is a pulse of 5 or close to 6, but more like a pull of 4 or so. Given this situation, one can make now predictions for other observables. In particular, one can make predictions for other lepton flavor universality ratios. Instead of looking only at Rk and Rk star, I can also look at R phi. That would be a lepton flavor universality ratio in B sub S to phi mu or B sub S to phi EE. And we can look at these various ratios, not only in this low Q square region up to 6 GeV square, but also at the higher Q square regions. And in all those cases, one roughly finds that the prediction, the new physics prediction, is that all those ratios should be around 0.8 or so. And what is shown here are the current measurements of Rk and Rk star, and it will be very interesting to see how those measurements will move with more data, and really very interesting to see how measurements, for example, of R phi will line up in this plot here. What are the implications for the new physics scale? So coming back to what I said at the very beginning, these anomalies, they in principle can establish a new physics scale, but what exactly the scale is depends on the assumptions one makes about the new physics coupling. So if one assumes that the new physics coupling is order 1, just some generic tree-level contribution to this BS mu operator, one finds a new physics scale of around 35 TeV or so. If I put in a CKM suppression or loop suppression or both CKM and loop suppression, one gets scales ranging from a few hundred or several hundred GeV to several TeV. If one pushes the new physics coupling to 4 pi, then one gets a new physics scale of around 100 TeV. But that's sort of the maximum that one can go. So in some sense, one can think of it as an upper bound of where one has to expect new phenomena to show up. So somewhere between a few hundred GeV and let's say 100 TeV, that's a range of possible new physics scales, possible new physics states or degrees of freedom that could be responsible for the observed anomalies. In terms of a simplified model, the model that I like most is a C prime gauge boson that is based on gauging the difference of muon number and tau number. That gives this vectorial coupling to the muons of the C prime, given just by the gauge coupling of that C prime, and that gives directly the Wilson coefficient C9 once one couples this C prime also to the quarks, for example, through mixing with vector-like quarks. That's a very interesting and versatile setup, and I know there have been a lot of work also from locals. I can look at various different aspects of these models. For example, the connection to neutrino masses, the connection to dark matter, and many other aspects. A lot of interesting things one can look at. One thing I always like to point out is that in this first paper we wrote about this model, it was actually before the measurement of Rk came out. So we actually had a prediction for lepton universality violation in this paper. So we originally wrote this paper to explain P5 prime before knowing about Rk and Rkstar, which came out a few months, or Rk measurement came out a few months after our paper. In any case, in the remaining few minutes, I see I'm running out of time. I will just go through a few aspects which I think are important in the context of this Altmannshofer model and the rare B decays. The first thing one can ask is, what is the viable parameter space of this model? What are the viable ranges for the Z prime mass and these and the corresponding gauge coupling that is shown in this plot here? In order to explain the B anomalies, the Z prime has to be heavier than the B mesons, and here just put some arbitrary cut of around 10 GeV, but it could be maybe slightly lighter, but maybe not, probably not much lighter than that. And once one tries to explain the B anomalies, one has to be careful not to violate constraints from B sub S mixing. If you have the Z prime, which has this flavor changing coupling between a bottom and a strange, you can have two of those couplings, and you will get B sub S mixing, and that constrains the parameter space down here. And then you get other constraints for larger G prime gauge couplings, for example, direct searches at the LHC, and then measurements from lab, for example, of the Z2LL couplings, which are modified at the loop level when you have the C prime present. There's also this CCFR bound, so that corresponds to a process referred to as neutrino trident production. That is dimuon production in the scattering of a neutrino on a heavy nucleus. And I wanted to make a few comments about this neutrino trident process, and there exist measurements of this process. So we have a mu neutrino beam which scatters on a nucleus and produces a mu plus mu minus pair, and measurements by experiments CHARM2, CCFR, and also by NewTEF have been performed in the past. And CHARM2 and CCFR, they claim they have observed this process, while the more recent measurement by NewTEF of this process, or the recent search by NewTEF of this process, they didn't observe it. They only got an upper bound, if you want, on the cross section of the corresponding process. And what we have been doing always is to show this CCFR constraint, which is the most precise measurement, which gives the most precise bound in this plane. But so talking to people at NewTEF, there's some doubt of if that is actually the correct thing to do. In particular, when one reads the corresponding NewTEF paper, they identified an additional background which was not included by CCFR and also not by CHARM2, as far as I understand. And in the NewTEF analysis, they had an improved signal modeling. And so there is the question of how reliable the older results actually are, and if they should be used to constrain the Altmannshofer tau parameter space. So maybe it is more conservative to actually use the weaker NewTEF bound in order to constrain the Altmannshofer tau parameter space. Anyway, this is just a sort of a side remark that I wanted to make in this context. A few more predictions concerning Altmannshofer tau. The smoking gun prediction of Altmannshofer tau is that one gets opposite effects in muon and tau final states. So this coupling of the Z prime to muons and to taus, it has an opposite sign. So if you, for example, reduce the B to S mu rates by a certain amount, you would expect that you enhance the corresponding rate into taus by the same amount, and the effect and the decay modes into electrons are unaffected. That's also the smoking gun characteristic signature of that model. The problem is that the decay modes with taus in the final state are very hard to observe experimentally. So with the current experiment LHCb, and then also with BEL2, they probably won't be able to have the precision to actually measure the tau final states and to see such a, let's say, a 20% or 25% effect as predicted by this model. A few other predictions of this model is there is no lepton flavor violation. So even though there's lepton flavor universality violation, there's no actual lepton flavor violation. So decay modes like B sub s to tau mu or B to k star tau mu, they are negligible, in contrast to many other models that have been constructed to explain the BDK anomalies. Also, this model predicts a purely vectorial coupling of the Z prime to muons, and therefore there are no new effects in B sub s to plus or minus. There one would need an axial vector current. So if this tension between the standard model prediction and the experimental results in B sub s to plus or minus becomes more pronounced, then this would be a way to rule out this universal tau model. But again, this is a prediction that is very different to many other models that try to explain the anomalies. And another interesting thing is that if you look at decay modes with neutrinos in the final state, so B2K nu nu or B2K star nu nu, in this mu-Mansell tau model, the muon neutrinos are suppressed, the tau neutrinos are enhanced, and the electron neutrinos are unaffected. But because one cannot measure the neutrino flavor in the experimental setup, one just sums over the various neutrino final states, and then one gets something which is actually standard model-like, because the suppression of the muon neutrinos is exactly counterbalanced by the enhancement of the tau neutrinos. So B2K nu nu and B2K star nu nu are predicted to be standard model-like to a very good approximation. And again, this is in contrast to many other models that are trying to address the anomaly. So this model makes a set of very precise predictions which can be tested experimentally. We tried to extend this model a bit to see if how robust these things are, and can, for example, introduce axial vector currents in this type of model also. That requires, however, CC prime mixing, or that will result in tree-level CC prime mixing, and is very strongly constrained. I'm running a bit out of time, so I will skip here the details. Want to show still this plot here that shows the future prospects for measurements of Rk and Rk star. So shown in this plot here is as a function of time, the precision that one can reach on Rk, Rk star, R phi, Rpk, which is the corresponding ratio with lambda b baryons, both at LHCb and also at Bell 2. This timeline, okay, this was done before the pandemic, so everything has to be shifted by at least a year or so to the right. But overall, there are very good prospects to have a few percent level precision for a large range of these lepton flavor universality ratios, both at LHCb and at Bell 2. And I think this would be a very important thing, that one gets a high significant for those anomalies for Rk and Rk star, both at LHCb and at Bell 2. And then in that case, I think it would be a very convincing case for a new physics effect. Maybe even Atlas and ZMS can say something in this context, but it's not exactly clear how well they will be able to measure the decay modes with the electrons. Another thing is that that can be done with enough statistics is that one can look at lepton flavor universality tests in angular distribution. So one looks, for example, at P5 prime in the case of muons and P5 prime in the case of electrons, and compares those measurements of P5 prime and sees if there's any difference between those. That would be another way of having an independent test of lepton flavor universality in those rare PDKs. Okay, that's my summary here. Sorry for going over a few minutes. So this several years, this BDK results, they show discrepancies with standard model predictions, and they persist with the new data. What is particularly interesting are these lepton flavor universality ratios, because they are theoretically very clean. So if the significance of those anomalies of Rk and Rk star in particular continues to grow with more data, then this would be a very clear indication of physics. And yeah, this recent Rk update from LHCb is reassuring in this context. And okay, if one speculates, maybe this is due to this gauged Newman's tau gauge boson. But in any case, I look very much forward to the next round of experimental results and to see how this story will go. Thank you.
Okay, thank you very much for the comprehensive talk. Are there questions or comments?
Do you have any comments on the RD star under the L-mu tau gauge hypothesis?
Very good. Yes. So for RD and RD star, the L-mu tau, the minimal model doesn't have any implications for RD and RD star. These RD and RD star measurements, they are related to this charged current B decays, the B to charge transition, and then the L-mu tau gauge boson itself doesn't have any appreciable impact on those. So in this minimal setup, RD and RD star just be standard model like. So there one would need to extend the model in some way in order to explain also RD and RD star. I mean, there are constructions where one has, for example, additional leptoquarks which are charged under L-mu tau, and then one can try to arrange things such that they might also contribute to RD and RD star. But at least in the middle setup there, it would be predicted to be standard model like.
Thank you.
Hello. Could you show again the preferred range of C9 and C10?
This one here?
Yes. Here, so the sky blue region is favored by Flavio. I mean, RK and RK star.
Yeah.
Which you mentioned has the smallest hadronic uncertainties.
Yeah.
And this orange line, orange region, from B to S mu mu. Does it include for example, P5 prime and branch ratio, etc.?
Yes, exactly.
Okay.
So if you look at the orange one, if you go back to the very beginning, I guess in this plot, I think the orange one excludes basically everything everything here. So the branching ratios down here and P5 prime, or all the other angular observables as well, all the full angular analysis and the branching ratio. So that part is included in the orange region, which is the part which has the least theoretical control, I would say.
Yeah. And then I think my impression is that somehow this sky blue region and the orange region does not overlap very well.
Yeah.
Well, maybe at 2 sigma level it should be okay, but
True. I mean, the RK and RK star, they do prefer this region up there, and the main reason behind that is that if you look at the actual numbers for RK and RK star, RK star is actually measured very low, so around 0.66, 0.69, while RK is around 0.85. And sort of this this difference in those measurements, that is that prefers this region in this in the upper right corner of the plot. So up there, you sort of can try to explain why RK is a bit larger than RK star, or why RK star differs in absolute value more from the standard model prediction. Down here, you're in a situation where RK and RK star are sort of more or less the same. So down here, the prediction would be that both RK and RK star would be around 0.8 or 0.85 or something like that.
Okay, so then the this red region is the combined analysis of all of them.
Yeah.
Ah, okay, I see. Okay.
So if you ignore the orange one, then the red region would move somewhere here.
Okay. I see. And your model for LU minus L tau with some vector-like fermions accommodate this red region, or just rough qualitatively?
Yeah, so the model sits actually down here. So it only has C9. It predicts that C10 is 0. So this model sits right down here at the
purely vector-like. Okay.
Yeah. So at the 1 sigma border of this range.
Right. I see. Okay. So did you include all this? I mean, how many data points did you use to get this?
I forget the precise number, but it's something around 100 measurements.
I see. So,
I mean, there are,
I mean, bean by bean, you.
Yes.
Okay.
Counting the individual bins, it's around 100. So there are all those processes. Each process has branching ratios, angular distributions. Each of those measurement is done in several Q-square bins. So if you just add all those up, you're something like 100 measurements that are included.
I see. Thank you.
Sure.
Further questions or comments?
Does your model provide any possibility of lepton flavor violating decays like mu tau?
One probably could introduce something like that, but it's sort of against the philosophy, I guess, of the model. I mean, I would say it's one of the interesting points of that model that at leading order, it would predict that there is no lepton flavor violation because of the gauged mu number and tau number. You sort of, in some sense, guaranteed that those at leading order those processes are absent, and I would consider this as a strong point of the model, that it predicts that unless you do something wild, lepton flavor should be actually conserved.
Could you say a little bit more about this? Your model you just showed briefly, but didn't have time to discuss. For example, I was wondering if you could also accommodate the realistic Euclid texture with I mean, how many numbers of Higgs doublet and so forth.
Okay, yeah, that's a. So we did look at neutrino masses, but it's complicated to do, at least when you only have one Higgs. So I don't think we looked at the case where you have several scalars. But if you have only one Higgs and then one scalar which breaks the symmetry, it's actually very complicated to get a realistic neutrino mass.
But maybe you may have to extend the Higgs doublet to write down the renormalizable Euclid interaction. But I'm asking this question, and I think this type of new gauge interaction is interesting if I mean, one can connect the flavor structure of Euclid couplings to this flavor non-universality in the BPs.
Yes, that's definitely a very interesting direction. I mean, I think what we try to do in this paper is just focusing on the aspects in the rare B decays and to see which type of contributions to the B2SLL transition one gets. And in this case, what we find is, for example, that now one can have effects in electrons, muons, and taus, and one can have sort of a free parameter which can shift the physics effect in any of those leptons, but still in a flavor conserving way. But the axial vector current that one gets, so the contribution to C10, one can have that. So one can have in this extension also a new physics contribution there, but it is necessarily lepton flavor universal. So the C10 has to be universal in this model, while the C9 can be non-universal, but you still have all those features that it is lepton flavor conserving. And yeah, if you try to explain, I don't know, for example, lepton mass hierarchies, or if you try to get a realistic neutrino mass spectrum out of that, then it starts to get more complicated. And I
see.
Okay, if there are no more questions or comments, we might expect Wolfgang again. Thank you very much.
Thank you very much for your talk.
Yeah, thanks again for the invitation. It was fun to give this talk, even if it is remote. But yeah, thanks again for having me.
Okay, bye bye.
Bye bye.
Right, bye bye. See you.
See you.